Okay. Okay. So now the goal of this lecture is to understand what reproduces the page curve, what unitarizes the black hole evaporation, at least in this context, in this model. I'm crucially going to use this picture that I can replace the bulk ADS2 region with the union of these left and right quantum mechanical systems. It is natural to use the following convention, as I guess I've been using. The black hole will be the union of L and R. The radiation is equal to BL union BR. And we want to show that this is the entropy of both LR and BL-BR. So we want to reproduce this. But recall, we computed what the entropy of BL-BR was. We just used regular CFT techniques in the bath system, and we found this ever-increasing entropy. I will address this issue later, and for now, define how I'm going to compute the entropy of LR. Okay. Okay. Now, there's a naive way of computing the entropy of LR, which is to just consider. Yes. Which is just to consider again, the same setup. So one naive way is to say, well, let me just consider the entire bulk dual of LR and just compute the entanglement entropy of this region. So let's call this region sigma LR. It ends on the two boundaries at some two given times. And so the proposal is then that entropy of LR is simply the CFT answer. The CFT von Neumann entropy of the subregion LR. But we know this can't be the case because by purity of the global state, this thing is just equal to S BL, BR, and it's.
Is LR on the left-hand side means of the space-like slice?
Yes. So on the left-hand side. So I'm saying there's a naive way of a naive guess for what the entropy of the union of LR is, and that guess is simply the CFT entropy of the space-like region that starts here and ends there.
The CFT being the CFT.
The bulk CFT. The bulk CFT. Sorry. Yeah. Yes. The bulk matter CFT. And I'm saying this is. This can't be the right answer because by purity of the global state, it's equal to the entropy of BL-BR, which we saw increases for all time, and this is the wrong answer.
Also, just because there's no Bekenstein-Hawking contribution.
Exactly. Essentially, this leads to this overfilling problem. The correct way, obviously, of computing this entropy is to do so holographically. And the most up-to-date version, so is to use the RT formula. And the most up-to-date version of the RT formula is the one due to Engelhardt and Wall, where one extremizes the generalized entropy. So let me go over that. So let's consider. Well, let me state the general statement, which is the entropy of some region R. This could be the right, or it could be any region R. Is going to be ultimately given by the area of some surface X divided by 4 g-Newton plus a bulk entanglement entropy piece of a subregion sigma xr, which is anchored on the region R on the boundary and ends on the surface X. So this is what it's going to be equal to, but which surface it is evaluated on, it has to be evaluated on an extremal surface. Extremal meaning it extremizes this functional. Okay? And in the event that there are multiple extremal surfaces, X, one simply takes the minimal one. Okay? The correct designation of this surface is a quantum extremal surface. So this would be a quantum.
This is the statement that we are doing it Cauchy slice by Cauchy slice. So when you first use this first extremal condition, that was on a particular Cauchy slice, which
No.
is an extension of the boundary time.
No, this has nothing to do with a choice of Cauchy slice. You're supposed to extremize over all locations of the surface in the space-time that are surfaces that are anchored to your region R.
Right.
Okay? This is separate from the maxi-min construction. Maybe that's what you're referring to.
It's not equivalent to that?
Yeah, so there are, I actually don't know what the status is of whether the extremization, the minimization is the same thing as applying maxi-min. So maxi-min is a statement that on every Cauchy slice, you take the surface of minimal area, and then over all Cauchy slices, you take the one with the maximum. Okay?
I hear that this is equivalent to that, but you are not committing.
I think so. As far as I understand, for the classical version, where there's no bulk term, you have just area. It's might have been proved, but I have this vague recollection of there being cases where they don't agree. Although I don't understand, I don't know. I'm not an authority on this on that topic. Whether there's a quantum version of maxi-min is currently work in progress. I know that Netta Engelhardt and Jeff Pennington are thinking about that question. So I'm not going to make use of maxi-min. I'm going to use this procedure of you extremize and then take the minimal one.
And then just to make sure I fully understand, so the idea is, we'll come to the minimizing over all X, but roughly is that you look for the Ryu Takenagi, you got some boundary region of interest, and you look for a surface which ends on that boundary region, and you compute the sum of the area plus you choose any Cauchy slice. Roughly given this surface, you get an entanglement wedge, and then you look at any Cauchy surface in that entanglement wedge, and you compute S bulk there.
Sorry.
Is that correct?
No, this thing can extend everywhere. Once you find the minimal extremal surface, that defines for you the entanglement wedge. So this thing can be anywhere. It can be, let's say, it goes all the way up there.
Can be anywhere.
Let me draw a few things. So this has some finite extent here. You can draw the causal diamond on the boundary, let's say.
Yeah.
That goes up to a point here and here, let's say. The causal wedge is what you get by shooting these guys into the bulk, and you get something like this.
So that's a different object.
It's a different object.
I agree.
Okay. Now you look for the quantum extremal surface, or the extremal surface, or the classical extremal surface, whatever proposal you want to follow. And this surface can be anywhere, but it has to be, okay, this is actually a subtlety, it has to be outside of the causal wedge. Okay. Let's say it's located there. Then the entanglement wedge is where you shoot null rays out of this surface everywhere. And what you find is that it becomes space-like at some point, and it joins this thing here like this.
The entanglement wedge is not just null rays coming out from that.
You get caustics. So you get caustics, and you're supposed to stop the evolution. So it's really, it looks like a thing like that.
So it starts off as null rays from C and then
Yes. So let's assume that this thing goes all the way out. Then this would be kind of a paradox, because a subregion outside R complement, can send a signal to this point. But, so that would preclude this point from being, in some sense, inside the entanglement wedge of R, because that's supposed to be only part of R, and nothing else can influence it.
But I see, I didn't realize, so then we should talk later, but you know, if you have entanglement, it doesn't mean you can communicate. I mean, this is, so I thought the fact
No,
that
that's-
the entanglement wedge could extend beyond the causal wedge would be okay with causality.
So, one statement, there's a notion of subregion duality. How much of the bulk can you reconstruct given a boundary region? And that has been answered, the answer to that question is that you can reconstruct everything in the entanglement wedge. So there are operations, there are operators on R which can affect the physics anywhere in this wedge, all the way here near the tip. So that's like this region here. And so there is an operator identification between these things.
But nevertheless, you are saying that, and I didn't realize this, that if you shoot null rays from the tip of that point,
From this thing.
entanglement wedge, the Ryu-Takanagi surface.
Yes.
Right? By the time they get to the boundary, they lie within or at the causal diamond.
Yes, they end on the causal diamond because of caustics.
Where is this? By the way?
Veronica Hubenet, I think, she discussed this.
Is there any formal argument just from the unitarity and probably large central charge of the CFT that causal waves should be inside the entanglement waves? Is there any?
That's an argument that uses the, if I'm not mistaken, the generalized second law. And things like that. But if you want a separate argument. Yes, there is an argument, which is that, let me see. So let's consider, okay, let's consider, okay, let's take the simplified case of having the left and the right, just to quantum mechanical systems. The causal wedge is just a bifurcation surface. Yeah. Let's say that the extremal surface for R extends all the way here. Okay. So now we don't have caustics, 1 + 1 dimensions. So this means, this would seem to imply that R is dual to a region here. You know, if we assume entanglement wedge reconstruction, then this part of the space-time is part of R.
So this was the end of the causal, end of the entanglement wave for a point on the left boundary.
So we said this thing is the quantum extremal surface for R.
Right now.
Since the state is pure for R and L, it is also the quantum extremal surface for L, but that point is not essential for the argument I'm making. Now, the statement of subregion duality says R is dual to this entire region. However, I can send a signal from L that can make it to this region. This would be a contradiction because the left and right system are not interacting. So this is the argument from.
I'm sorry, I have a more elementary question.
Yes.
I haven't understood your. So you want to compute SLR. So you want some surface that surrounds LNR. I mean, the usual Ryu-Takanagi formula.
Yeah.
It ends on the boundary at some points on the outside of LNR.
Indeed.
Now, LNR were both points.
Yes.
So I suppose your surface ends a little bit on the path on the side of left and a little bit on the path on the side of right. And then it can either join up or just disappear somewhere in the path. Is this right?
Ultimately, that's going to be the answer, yes.
But the rules are that it has to have endpoints a little bit to the left and a little bit to the
They don't have to be. It can be right on L and right on R.
Okay, I'm regulating that.
Sure.
Okay, and then can do whatever it wants.
Of course, of course.
Okay, thank you.
Yeah, yeah.
So yeah, that's exactly good. And just to ask what Aviv is asking,
What?
even,
Yeah,
so
yeah, go on.
I was putting it in terms of entanglement wedge, but never mind, forget that. You have the boundary curve of the Ryu-Takayanagi surface.
Yes,
And then you can fill it in many different ways
yes,
to obtain a surface sigma.
yes.
And so,
Sorry.
what is the rule
Yeah, yeah.
for sigma? Is it
Doesn't
that
matter, anyone.
It doesn't matter because it's a space-like slice.
Yeah, 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 yeah.
But within it's a space-like slice, right? That's good enough.
The von Neumann entropy of any region anchored to the same sort of boundaries has the same entropy.
But it will not matter as long as it's the same.
Sorry, in your this picture then, suppose I put a operator which is like OL OR, then this will go inside here.
OL and OR can do whatever it wants.
Suppose I put a interaction in one of the sites at OL times OR,
Yes?
then the entanglement wedge can go in.
Yeah, it can do whatever it wants to do.
Because
There would be no contradiction in that case. Yeah, yeah, yeah.
You know, then again, maybe we can discuss this offline, but as you mentioned, and this is the setting up it most, in 1+1D there are no caustics or anything.
Yeah, so that's why I was able to just evolve it normally.
Just the fact that the quantum extremal surface goes in, doesn't it mean it goes beyond the fact that it lies inside the order, doesn't it mean you're going to be able to,
Sorry.
through causality, connect on the outside? Yeah, what
Sorry.
do you say here? Yeah.
This is a counterfactual case. You don't get, so this is the case where L and R are not coupled. I was showing that there's a contradiction. If you assume that the quantum extremal surface is contained in the left exterior. The contradiction being is that L can influence this region. That's in contradiction with this region being dual to R. That's all I was making. Okay.
But how does that even go about saying that it implies that your causal wedge should be inside entanglement wedge? Like, is that it? My question was about that. That can you somehow
Because this is an example where the entanglement wedge of L is contained inside the causal wedge of L. Right? The causal wedge of L is this. The entanglement wedge.
the whole of L.
Sorry, these are different pictures. This was a spatial slice. This is time now.
Right. So you say one-dimensional boundary. At a constant time slice, you have a point. So your point
Yeah.
is the whole of space,
Yes.
and you want to calculate entanglement entropy of the point.
Yes.
Let's say this is what you can do, and then in the two-dimensional example, on the boundary you had a boundary domain of dependence.
Yeah, but here I have the entire thing. Sure. The boundary domain dependence is all of L. Is the entire history of L.
Yes. So in this case, the causal wedge is for the left CFT. Causal wedge for the left CFT is the whole of left inner wedge.
Yes.
And if this is the case, so you said that this is an example in which your causal wedge is larger than the entanglement wedge for the left boundary.
It's a counterfactual example. It's not a real example. Let's assume that it's true.
If
Then
it was the case, then you would have said that there is a contradiction.
yes, there is a contradiction here.
Right. Then this sort of says that it couldn't be happening.
Yes.
But it's not the most general argument in some sense.
Sure. I think this argument is actually very general. It's actually very, very general. Whenever the entanglement wedge is inside the causal wedge, this means that there's a region inside the causal wedge which is contained in the entanglement wedge of the complement. And since I can influence it, that's a contradiction. Yeah, we can talk about this offline later, but I think it's a general statement. Okay.
Your point is that you can't influence the entanglement on the right-hand side.
Exactly. Yeah.
So basic questions. This prescription here is, I can make sense of this for when the boundary is one or higher dimensional.
Sorry, which statement?
I can have anchor points.
One space or space, right?
One space dimension.
So I missed the first part of the question.
This prescription I can make sense of it
Mm-hmm.
When the boundary is two-dimensional,
You can make this. This makes sense in any number of dimensions.
two or higher dimensional,
Okay.
but when it's less dimensional,
When you say
Yeah.
you mean space-time or something?
now space.
Space-time.
Yes.
So you're worried about 0 plus 1 units.
Yeah.
That's correct.
Yeah.
How
So
do you surround a point?
when you don't have anchor points, I mean, when you're one-dimensional, okay,
That's the example I'm going to talk about now. I mean, that's yeah.
Dimensional boundary.
Let's erase this.
It does make sense even there.
It does. Yeah. Well, I don't see why not.
Yeah, but the anchor point is better.
Okay. Let's consider an example, which is the eternal black hole.
You just take the corresponding point inside, which is all of the boundaries here. It gives you some kind of boundary.
So the application of this rule here is the following. So you have to extremize this surface. Okay? You have to extremize about the location of this surface. So it makes sense in the following sense. As in, this is now a 1 plus 1 dimensional bulk and 0 plus 1 dimensional boundary. There's a surface here. There's the area, which is just a dilaton divided by 4g Newton. And the surface sigma is simply this surface. Because it's the coefficient of the Ricci scalar term in the action. That's how it comes about.
Okay, but I can, yeah, I mean, by anchor point, you didn't so much mean R as the anchor point for the Ryutakyanagi surface, perhaps, right?
yeah, there is
Is
no
that
anchor
what
point,
you
that's the
asking?
whole thing. So even in the higher dimension, I would imagine if you want to compute the whole of the thing,
Yes.
then it just from everywhere it just comes out.
Yeah.
And forms an annulus.
Mhm.
Is that the case?
Yeah. It has to be homologous to the boundary.
Yeah. Okay.
Yes. I didn't mention that.
Yeah, but then why is that R not allowed to move in?
R not allowed to move in.
You got 1 point.
I'm computing the entropy of R, and the prescription is you're supposed to look for other points in the bulk that are homologous to R in the sense that they bound the same
So
region.
the point is just that point.
Yes.
And that line there is
Arbitrary.
Arbitrary.
That was the point that
Yeah.
in sigma it didn't matter.
Yeah. And you're supposed to.
This is always codimension 2.
Right.
So therefore, in this
Yes. The point is codimension 2, exactly. And the extremization is you're supposed to extremize over the location of x. So take the derivatives with respect to the location of x, and you set that to 0. And you're supposed to extremize over all possible locations, search everywhere in the space-time, and cross your fingers and hope that you land in some place that makes sense. So if you apply it in the eternal black hole, you find that x lands on the bifurcated horizon as you expect. Okay? Good.
So in which case you expect here, you said?
In the thermal field double state, the eternal black hole, it lands on the bifurcated horizon, essentially because of the symmetry of the problem. Okay, but now we want to apply this for our case here. So we have to look for surfaces that end. Let me see. So in the same sense, so okay. Let me draw the surfaces and explain why those are the ones we have to look for. So one candidate surface is the one that looks like the eternal black hole case, where this is let's call this sigma Lx, and this point here XL, this point here XR, and this interval here sigma LR. And
Sorry, maybe you say this, but how do you construct the sigma LR? I mean, it's not just a space-like thing in which you just draw a line.
Good. Good. So this depends. It depends. So we're trying to apply this prescription to compute the entropy of the boundary at some given time. Okay. So let's say we want to compute the entropy at this time. Now we move these points anywhere we want, and again, the entropy of sigma LR will not. It doesn't matter which slice we take. Right. So let's say we fix this point here. So it doesn't care which sigma LR. It doesn't matter which sigma LR I take. It'll give me the same entropy. So one contribution, it looks something like this, where the answer is going to be phi at XL divided by 4g Newton plus phi at XR divided by 4g Newton plus the bulk entropy of the union of sigma Lx sigma R X LXR. Okay? So that's one contribution, which looks a lot like what we had here. There's an interesting thing where the S bulk is it's the entropy of the union of the two regions. Okay? So that's one candidate surface, and we need to extremize over the locations of these points. This I will call the disconnected surface. Okay?
So there looks like a lower bound to where XL can go, right? It cannot go inside a light cone.
It can, yeah, that's right, that's right. So it has to be inside this so-called Wheeler-DeWitt patch. You have to extremize over all locations such that sigma is space-like.
So it can go all over also the inside the black hole.
Wherever it wants.
This approximation is that the matter has this approximation is valid when the entropy of the matter, the conformal matter in the bulk is small compared to.
Yes, yes. So it seems surprising as to why did I even write that term? Why is it ever going to be important? But it actually isn't. So the punchline is that the value of S bulk is small, but the derivative can, well, yeah, the derivative can be large. But that's actually, that's a frame-dependent statement, right? We're taking a derivative with respect to some coordinate. So what it means to be large and small is not really an invariant thing. But nevertheless, it's an important contribution.
But I mean, in your semi-classical approximation where you take Gn to 0 and n to infinity, the two will be comparable, right? Even in parametric scale.
But then why isn't there another term?
Which one?
This is like one loop.
No. They're never going to be comparable.
Why is that? I mean, there's no parametric separation.
I will give you. We did the calculation, and
I know, but okay, maybe in some specific instance, but just parametrically, both are comparable in like semi-classical.
so why? Sorry, can you explain to me why this thing becomes large?
The S bulk is enhanced by n, right? Or
No.
central charge, right?
No, but we're working in the limit where 1/g Newton is much larger than the central charge.
I thought you were working in the limit where central charge goes to infinity, Gn
No.
goes to 0, keeping the product fixed.
No.
Well, I mean,
Oh, sorry.
that's the limit in which the formula you wrote down in your first
Sorry.
lecture is valid. No?
Can you say the limit again?
Central charge goes to infinity,
Yes.
and G Newton goes to 0,
Uh-huh.
keeping G Newton central charge fixed.
But how big is this?
That's up to you.
Yes, so good. We're working with this being,
Parametrically, it will be order 1, but of course you can take it to be 1/1000, which you do in your paper.
why can't I say I take this? Why? Let me see. I'm confused about why I need to take this to be infinity.
Well, you want to take Gn to 0, right?
That's fine, yes. But why does C have to go to infinity?
Because if you literally kept it to be finite and you took Gn to go to infinity, then the second
Zero.
term would be just 0 parametrically.
But the claim is that even in that case, it can contribute.
I don't think so. I think the limit you actually worked in, at least in your paper,
No,
is this one where Cgn was a small number but not parametrically scaled.
So if I give you a free theory, just a free scalar field in 1 plus 1 dimensions, C is equal to 1.
I don't think in that limit,
No,
in that theory, your calculations are valid in any genuine way. You need a theory, if I may say, where you have n scalars,
Uh-huh.
free, and then you take n to go to infinity with gn going to 0 in this way.
I don't think, I think I disagree. I think this applies even if I just have a free theory.
It could be free, but you need n scalars.
No, with C equals 1. I don't see where that comes in.
Then any effect due to the bulk is comparable to a one-loop gravitational effect. See, because the one-loop gravitational effect is order 1.
But what's the one loop gravitational effect here?
So that we have to compute, you have to quantize gravity.
No, but there's no gravity here.
No, it is. There's 2D gravity. 2D gravity is non-trivial. I mean, Liouville gravity is non-trivial. See, you've kept
I see. You're saying
solve the Einstein equations with a right-hand side due to matter.
You're saying there's a quantum piece coming from like the Schwarzian, for example, that might compete to this?
Yes.
Although
Or the quantization of the not the classical part from the Schwarzian.
that's right. Though I suspect, so that's a boundary thing in some sense. And I suspect that it does not care sensitively on the location of the quantum extremal surface. But ultimately what's going to happen is that there's going to be a sort of some balancing effect between the area term, the gradient of the area term with the gradient of S bulk. And I just suspect that we can imagine that there might be another gradient term coming from the quantum Schwarzian, which will be subleading, is my guess.
You
But
have to show that.
of course.
What I'm saying is you're perfectly correct in your paper, you're not worrying about it, in the limit where n goes to infinity as well.
Sure.
That's all I'm saying.
I see. Okay. Fair enough. Okay, so I was talking about the different kinds of surfaces. One surface was the disconnected surface, which looks a lot like the thing that we drew there.
I'm sorry, but just a general question, not to slow you down, but this formula in principle has some second correction.
Yes, there's an expansion. There's an expansion in G Newton. There's an H bar expansion, and this is the first subleading term in that.
And so then if these two compete in whatever gradient or whatever, you will also need an argument that the next correction does not compete.
The next correction is subleading in G Newton, or you have some other
And
correction?
that is provided in this limit I was saying,
Yes.
that is parametrically given by, it's a 1/n correction.
Yes.
So you had only those corrections, Mike, or some other corrections? This G Newton correction and 1/n correction?
Yeah, I was saying that there's some physical effect and some physical configuration where you're balancing two things.
Yes.
You want to make sure that balance is not ruined by it.
Indeed. And that's where Sandeep's comment saves the day.
So the H bulk is ordered G Newton to be 0, right? This H bulk.
Correct.
So and that is compensated by a C factor of C that comes here. Is that the point?
No, C G Newton is still very small. C times G Newton is still very small.
It's a fixed, he keeps it small. Actually, you could repeat your calculations even if it being, not very small. It is just computationally harder, but it doesn't
Sure.
It's all a valid
Sure.
Anyway, so he keeps CG fixed, but it's small.
Yes.
But can I ask you one thing? Because
Yes.
this formula is kind of important in finding the quantum, in the whole story as it goes. What's the proof? Netta, Engelhardt, and
I think
given it, but what's the real proof for it? If I may ask?
the real proof.
I mean, how solid
So
Ryu Takenagi we know, because this might anticipate what you'll say later. Ryu Takenagi, without the corrections, comes out due to the replica trick, because
Yes.
of Levkovich and
Yeah.
all the Senna.
now just include the matter term as well.
And you would just include, in the bulk, the quantum effective
Yeah,
action.
that's right.
Instead of just the minimum. And does that give this?
Yes. Okay.
So if you have a CFT dual to which there is say gravity radius, and then you make it coupled to some matter fields in the bulk, then even while computing the entropy of the CFT region, you
The bulk
But
fields, you
when
mean?
we talk to the bulk diagram would still contribute in this way.
Yeah, I mean, those are dual also to the boundary CFT, right? So their entropy does contribute, yes, in this way. Okay, so I explained the disconnected surface. There's also the trivial surface, which is the one with no dilaton contribution, and that's simply the entropy of sigma LR. Okay, that's the trivial surface. That's why I left it up. So this is the trivial surface. This is what the prescription tells you. You're supposed to look for all, that's sort of what you get when these points sort of come together and in some sense annihilate. But you're supposed to look for something which is homologous to LR. This is trivially that.
So if it has no endpoint in the bulk, you don't add the area term.
There's no area term, exactly.
If you separated this a little bit, you get two area pieces.
Exactly.
Yeah, so it's very delicate. Exactly.
Yeah. Yeah. Sorry? Yeah, so again, you're computing the entropy at a given time, and you're supposed to anchor these guys at that time.
Yes,
So-
so if I went to future time, not t equals to 0.
Yeah, it'll just be like that.
And
Or-
the idea is that will extremize. Is that correct? What
Yeah, that's already an extremal surface. Because taking the derivative of the dilaton, the location of the dilaton, it returns 0 because there's no dilaton. Yeah. Okay? Very good. And I will not do the calculation for this case, but I'll tell you what the result looks like. So, let me see. Yeah, the reason why I won't do the calculation is because it's not universal. There's an entropy of union of two intervals, and that depends. So there's a non-trivial cross ratio, so it's theory dependent. However, I should say that even with that, in the limit of late times, you can kind of see that the cross ratio is going to 1 or 0, depending on how you define it. These 2 points are approaching each other, I claim is what's going to happen.
Cross ratio of what?
Here the S bulk term is the von Neumann entropy of 2 intervals in this under some state of CFT on this entire slice. So there are 4 points. So there's a non-trivial cross ratio. I claim that at late times, something that will happen is that this term becomes the sum over S bulk sigma LXL plus S bulk sigma R XR. Okay? So it looks like now it's the extremization problem is a separate one for the left and the right. And let's assume that you find a surface, because of the boost symmetry, it's going to be the same surface for all time. So it's going to give you a constant answer. So that's going to reproduce something like that. Okay? Okay. Now the thing that you find, it's a constant answer, but what is that constant? You find that the surface is located very close to the horizon. So there's a locus of points that looks something like this. And so for this time, it's this surface. For this time, it's this surface. For this time, it's that surface, and so on. And it's very close to the event horizon. By that I mean, in terms of this Schwarzschild coordinate, it's or rather, let me see. So the Schwarzschild coordinate goes to infinity, the one that I defined last time at the horizon. So let's say that it's very, very large. So basically to leading order, the dilaton is just given by the value of the horizon. Okay? So
What do you mean? Dilettante is given by?
the value the value of the dilettante at the horizon,
Which is something fixed. all
which is
over the
fixed. Yes. Right? Because we have a static situation, right? And so so this way, you get.
Sorry, just one trivial question.
Yeah.
So I thought the extremal surface you just said, maybe I misunderstood, is that the constant this times this line, right? The parallel to the.
That's one. There's another one.
That's one.
Two.
So
That's a separate.
so I've been discussing extremizing the disconnected surface. Okay, and you find the claim is that at late times, the quantum extremal surface is located at some given Schwarzschild radial coordinate for all time, and therefore it's a constant. And the value of that constant is roughly, so we have two dilettante terms, so it's 2 times the dilettante at the black hole horizon over G Newton. Over 4G Newton, plus corrections, okay? So it reproduces that expectation, that it's equal to the Bekenstein-Hawking entropy. Remember, the Bekenstein-Hawking is double the area.
And the matter part is not important.
The matter part is not important. It's a small term. It is important in the extremization procedure of finding that this surface is extremal. We know that this is not classically extremal, right? The only classical extremal surface in this space-time is this point.
That would have given the same answer.
Yes, but it's not a quantum extremal surface. Okay.
Last correction, because this sigma surface is not exactly the horizon itself. Is that correction?
Yeah, there are two corrections. There's that it's not exactly the horizon,
Yeah.
and I also ignored the bulk entropy piece. Right, I have to include this piece, right?
Oh, yes.
Yeah, so it's there as well, but it's small.
That was
It-
log of G Newton on it?
It goes as C times log. I'm not sure what it is. It might, so the way that we wrote it down, yes, it was actually log C times G Newton. Yeah, I think it did involve something like that. Okay.
The fact that you got 2 is pretty interesting.
Yeah, so they disconnect. They disconnect in this sense, that it becomes a separate extremization for each side. And because of the boost symmetry, it's a constant.
I mean, in the sense that if you didn't have the bath and you looked at the thermofield double, then you would have got 1 times 5 BH over 4G Newton
You mean if you computed the entropy of one side?
on one side.
That's right.
And 2 sides you'd have got nothing, presumably.
Because
Yeah, I would have thought.
Oh, sorry, are you talking about this case, or are you talking about the exact thermal field double?
I was saying, suppose you took your system through the bath away,
So the usual eternal black hole, okay?
then you would have got, 1 times 5 BH over 4G Newton
Yes.
plus some log term.
That's right.
To the extent you're not worrying about the log, you've got 1. And
Yes.
here you get 2.
Yes,
And it's because each side is,
yeah.
tangled with the radiation.
Exactly. The density, in some sense, the density matrix of the left and right has now has factorized.
And gotten entangled.
Exactly. Okay, there's an interesting observation here, which is that the quantum extremal surface is outside of the horizon. Right? So it's the union of this surface and this surface. It's outside the horizon. So nobody threw any tomatoes or bananas at me. It's inside the causal wedge. Right? So it seems to contradict, what I was saying before. And there's a question about why don't we run into a contradiction. Let me keep you guys in suspense and talk about this later.
But I thought inside is okay in that the causal wedge, that means entanglement only probes some of the sort of region. There's more information in the system than just entanglement.
No, but if entanglement wedge reconstruction naively says that your system is only dual to the part of the bulk up to the entangling surface. Everything else belongs to the complement, whatever the complement is. So this seems to say that, so I mean, let me spoil the punchline. The interior here is dual to the dual to the radiation. But
Upstairs and downstairs further on, if you draw the Poisson Lewis for the complement, let's say you take the right one and then, left one, and then draw the for the complement region. I
Okay.
get the 2 point by looking at the
let
complement
me
region.
let me make my statement first, and then get back to you. So the statement is that so naively you might have said that LR is dual only to the union of this region and this region, and somehow the bath is dual to everything else, right? But I could have sent a signal from the, let's say, from the right boundary that propagates here. So it seems like I can affect this region, which is supposed to be dual to the bath. Is that not a contradiction? Answer is no, because in this setup, the bath and the right are actually interacting, right? They're coupled. They're not like the case that I was talking about before. So there's no surprise that the information that I sent in is contained there. In fact, this is a manifestation of the Hayden-Preskel protocol, right? That I can send something in from R, and at some point, it's lost to L and R. It's contained in this region, which is part of the entanglement wedge of the bath.
Actually, I was going to say more, that this proves that your ideas of the firewall are not needed, because the inside are being reconstructed by the radiation.
Yeah, but I didn't give you the argument for that yet.
Okay, fine.
Okay?
I'm uncomfortable about the use of this ADS-CFT.
Okay.
Because Sandeep says that you cannot ignore the two loop terms unless there's a lot of matter. The number of matter field scales with G Newton. But that's traditionally when ADS-CFT doesn't apply.
No, sorry. No.
What did you mean, sorry?
Normally the number of bulk fields is held fixed as G Newton goes to 0. But you're taking the bulk matter to scale with G Newton. Usually that's no good example of ADS-CFT.
So that's why I was not.
That's certainly true. I mean, okay. It's not supposed to literally apply. The semi-classical limit here doesn't literally apply.
How about weakly coupled string theory?
What?
How about weakly coupled?
No, take an energy scale. Under any given energy scale, finite number of degrees of freedom as G Newton goes to 0. The fields in the bulk shouldn't.
No, finite, but you can take the limit where the tension becomes small as it becomes weakly coupled, and then you could bring the string modes down with the gravity becoming weakly coupled together, right? It's some weird limit, but I could consider that.
I mean, we know it's like free angle limit. We can count the operator spectrum.
But it should be done in a scaled way, right? Not just.
Work in units where the sphere is radius 1. In those units, you fix any energy. Number of states is fixed. It doesn't scale with it. Anyway, we can come back.
I'm just saying, just as a 2D theory, this is the limit in which I understand, not worrying about whether there's a hologram or not. This is the limit in which I understand why these terms are kept and no others. Otherwise, there should be other terms in general.
No, but I'm just worried about them using ADS-CFT for that. ADS-CFT applies to bulks, certain kinds of bulks. This is not that kind of bulk in my opinion. But
So this is a question of how big does C need to be,
yes,
and yeah.
If it's not parametrically small, but just small. That is n times gn is 10 to the minus 4.
yeah, then we could discuss.
Yeah.
Yeah, I suspect, again, going back to that point, that even if we take C being small, that maybe the quantum piece from the Schwarzian would not contribute because this extremization is a bulk thing, But it is something to investigate further.
I mean, it could be, but, you know, something we wanted to do also, but
Okay,
it
okay.
hasn't been done, so.
Okay, very good.
Also, is there any example of it where the CFT in the bulk as such, when the gravity becomes weakly coupled that you see a CFT?
Not that I know of, but it's, yeah, actually. There are near horizon limits of charged black holes. Certain kinds of matter do look like 2D matter, 2D CFT deep down the throat.
Sorry, what was the question? Do you actually get this kind of 2D matter?
Yeah, 2D CFT.
Yeah, so if you take a magnetically charged black hole and you look at fermions, then there is one mode of the fermion which literally behaves like a 1+1.
Yeah. Okay. So we found two candidate surfaces. There was the disconnected surface, which at late times was a constant, and there was a trivial surface, which is the entropy as bulk. So we have these two contributions, and the minimality constraint on the entropy tells you that you take the minimal one, and lo and behold, we got the Page curve for LR. Okay? With the factor of 2.
So it's twice that.
This thing is twice the Bekenstein-Hawking entropy, if you will, or however you're defining the Bekenstein-Hawking entropy.
I mean, there for just SPH.
No, their SBH was half of this SBH, or double this SBH. So the SBH here, I mean twice the dilaton at the horizon of 4G Newton.
For his thermophile double coupled.
Yeah.
But that was the a priori expectation that it's
Yes.
twice.
That's right. Because, so we have a wormhole, so we have two horizons.
So the extremal surface that should lie outside the light cone, outside the causal thing, does it require strong symmetry to show that, or?
I don't know, maybe. No, maybe you can, the way that there might be a proof using that, but there's another proof that I discussed earlier just by causality, I guess. That in the case where, let's say, I don't know if I should repeat the argument, but it seems like you can send information to a quantum system that you're not coupled to. That was the problem. Okay. So the way that we got the Page curve was, let's recap. So we computed the entropy of the black hole, and we got the correct anticipated answer. And it came from the fact that we had these two different contributions, and the minimality constraint took us from one to the other.
So what I was asking is that don't you already have assumed that inside the black hole mode and this boundary is already coupled? Otherwise, you would have got again the problem of firewall, etc., here.
No, but you see, I computed the entropy in a different way, right?
Yes.
I'm just there's a prescription to compute entropy, which is the Ryuta-Kanagi prescription, and I just blindly apply it to this case, and I get the right answer. How this meshes with arguments of Hawking and Hawking radiation, and the entropy has to increase and so on, is an interpretational one, which we'll get to. But it seems to say that somehow the left-right system is no longer dual to the interior. So the entanglement between the Hawking modes outside and the things inside don't contribute to the entropy because they're not they're not dual to the left-right quantum systems. That's why we don't include them. Yeah. Okay. Okay, and we computed the entropy of the bath, and we got the wrong answer. So we did two calculations. One gave us the right thing, the other one gave us the wrong thing. And so, we have not, quote unquote, solved the information paradox, at least yet. The idea now is that we need a context in which the entropy of the bath can be computed using holography, right? Holography was a key ingredient here that gave us the right answer. And so I'll consider a model in which that's the case. But before I do that, let's do some answer analysis. Let's see what the answer should be, and then see how we can get it. Okay. So the idea, so we know that SBLBR must equal to SLR, right, by unitarity.
I got confused a bit.
Yes?
So right now we produce this entropy for the black hole,
Yes.
for the bulk, right, which goes like this.
Yes?
This and then goes like that?
Yes.
And what happens to this piece that was constant before the page time?
It was subdominant.
Yeah, well, it was subdominant.
Okay, so the right answer is this one.
Yes.
I see. But at some point, yesterday we were discussing how it's boost invariant and then you should see the same mass for the black hole at all times and so on.
Yes, but I don't see why that's relevant. That is just a statement that it's pretty much constant for all time.
But before the page time, it's not.
The entropy of what are we talking about? Are we talking about the contribution coming? So there's a locus of subdominant quantum extremal surfaces before this time that looks something like this. Okay? And the value of the entropy here is more or less constant for all time.
Anything boosted value tells you anything that is side by side there.
Yes.
Things that talk between two sides don't have boosted value because you're moving both the sides.
Yeah. To leading order in n, it's constant for all time, but because of this thing, the bulk entropy piece actually evolves with time. Okay, so we want to get this guy. So we can conclude, we can sort of find the what the answer should be for BLBR in the following way. Essentially, I already said this, but so we know that for when computing SLR, we had two possible surfaces, this thing plus something like this. But this entropy should be equal to the entropy of the bath, where in some sense, if we compute the entropy of the bath, which is this region, that so the entropy of LR, the trivial surface contribution is equal to just computing the entropy of the bath, the union of this thing and this thing. But at late times, it's equivalent to computing the entropy in this way. Right? So these give you the same answer. So here the idea is that you're computing the entropy of the union of these three regions. So there's the bulk entropy, and then there's the dilaton contribution there. This is the complement of this region. I'm just filling in the gaps. Okay?
It's the complement, but you have extra dilatons.
Yeah. So this also has a dilaton piece.
There is a dilaton, but you don't add the dilaton piece at the end.
Oh, there's no dilaton piece here. As Shiraz wanted to do, let's imagine that we're regulating this. There's some cutoff a little bit in the bath region.
Okay, I see. Oh, so wait, let me understand if I'm a bit confused about your right-hand side diagram. That's supposed to be just bath.
This is what the answer should look like for computing the entropy of the bath.
And now you need something that will justify it.
Yeah.
Exactly.
This is what it should look like with only the dilaton added at that in the middle.
Yeah. So let me put a circle around them.
Fine. Yes, that I agree. That's what it should look like.
Yeah.
Well, why
Looks-
only this? Also the bulk of the bath.
And the bulk, yeah. No, I meant the dilaton's not at the bottom.
Okay. So the idea is that the entropy of the bath should always be the complement of the entropy of LR. And so at late times, it predicts that if you compute the entropy of the bath, you have to include a contribution in the bulk. And so,
By hand, it should come out, right? That's what
yes. So we should derive this / find a model in which this is true. So it seems to, so if we were to write down what the equation is for BLBR, this is von Neumann entropy of BR union I plus the dilaton on the boundary of I, where I is that region in the center, which I will call, I will denote as an island. Okay?
So before the break, we talked about how A tilde, sorry, maybe this is like
No, go on.
A tilde could be part of the Barth-Hilbert space.
So A tilde? Yes.
So is this going to be a manifestation of this thing?
This formula gives you that actually. So this
But
formula,
now this I is outside, has some pieces outside the horizon also.
yes.
Is that not an issue?
So we should be careful about things that happen in this region. While the two systems are coupled, perhaps one cannot make a precise statement about which part of this is dual to, perhaps there's not a precise statement about the degrees of freedom near the RT surface, but whether they belong to LR or to the bath. There might be an issue there. To actually check, what you should do first is decouple the two systems, then compute the entropy, look for the quantum extremal surface, or rather look for the island. And if you land on this, then wherever that island is, then you know that that part is actually dual to the bath. Okay? But what will happen actually, as soon as you decouple the two, the mere process of decoupling injects some energy into the system.
Decoupling of the boundary CFT
Yes,
and the Barth?
exactly. That inserts some energy into the bulk, and that actually forms a horizon. And then you find that the horizon looks something like this. So this island gets hidden behind the horizon.
That's very interesting. I see. So if you try to decouple,
Yes,
the island is hidden.
yes. It's this crazy thing. It seems like just enough energy. Gravity knows about these things somehow. Yeah. So, yeah.
I was going to exactly make this thing that now I know you're going to evoke gravity, but I mean, you just take the state of the bath by itself.
Yeah. And this thing, so this formula actually tells you that the interior is dual to the bath, right? I can put a qubit here. Shiraz doesn't like qubits, but I can put a qubit there, which is in some mixed state.
Say that you can put Alice in there.
But then it sounds really weird because I was going to say I'm going to put Alice there in a mixed state. What does that mean? Okay, so a qubit there in a mixed state. This term here is sensitive to that, right? It's going to increase by log 2 or whatever. This tells you that there's a mapping between the Hilbert space here and the Hilbert space of that. So you can do something here which affects that. This is, the precise version of this is called the JLMS relation, the fact that relative entropy in this region is equal to relative entropy on the boundary. And this was proved by Harlow, Dong, and Wall, that the JLMS relation implies a duality in terms of operators. That the operator that changes the state of this qubit here can be mapped to an operator here. So it establishes a dictionary.
So that whole Hilbert space, or to the extent there's a Hilbert space in the middle,
Yeah.
is entirely created by the outside.
Indeed. Assuming modulo these issues about the extremities, say we decouple first. Yes, exactly.
And that's consistent with sort
Yeah.
of what you were saying there, that
Yeah.
as far as L and R are concerned, the entanglement wedge or whatever, that line, sigma L only went in outside the horizon. It's not even up to the horizon.
Yeah, yeah. Also, let me,
What that means, you might have at least thought you could recreate up to the horizon in the boundary LNR, but even that part of the outside region is in the radiation.
yeah, yeah. This is, yeah, maybe, I don't know if I should say this now, but, I mean, I didn't derive the formula yet, but we're just analyzing it. But since we're talking about it, let's consider the case of, zero temperature, okay? So in zero temperature, let's ignore there's no left-hand side, we only have a right-hand side. The spacetime looks something like this. This is the extremal horizon, and this is the bath. Let's compute the entropy of, the bath like that. You find the island, the corresponding island. Well, first of all, you find that this thing has an island. It's already a non-trivial thing. It's that. So this says that if you have a near extremal black hole, an extremal black hole, so something like this, the physics deep in the throat, past some point here, which is actually very far down, is somehow dual to the exterior region. The physics down the throat, far in, is actually determined by the IR physics far away, outside of the throat. That's what that says. Yeah.
When there is no coupling, these things are decoupled, you would want that to be hidden behind horizon.
There is coupling here.
There's coupling.
Here, I'm imagining that I have a quantum mechanical system here, eternally coupled with a bath, but everything's at zero temperature. I'm saying even in this case, you have an island that looks like this, and so the physics deep down the throat is dual to the exterior. Yes, I agree. But we'll get back to this after I explain the model. Questions? Okay. Shiraz, you were going to say something.
No, forget.
Okay. Last thing I want to.
One comment is organization. One Gautam has to leave very soon.
Okay.
I suggest we soon wind up for today.
Are we going to need 2 more lectures? I'm just asking. I mean, tomorrow is
Um,
only one because we have some unit test.
Other unit, we have a department meeting at 2 today.
Yeah, so today I think this also exhaustion will mean we have to stop.
But can I make the last comment?
Yeah.
Okay. The last comment is, maybe this is clear, but this explains why the entropy of the bath is small at late times. Because now you have Hawking radiation that comes out. That is entangled with radiation there. When you compute the entropy of this, that includes both Hawking quanta. And that's why the late time Hawking evaporation process does not increase the entropy.
It's your A tilde story.
It's my A tilde story. That was the comment I wanted to make. The next discussion was to start to introduce this holography within holography example. Maybe this is a good place to stop.
I mean, you're going to do this calculation or you're not going to do it? I thought you were going to do. Oh, that's your holography.
Yeah.
Okay, good. No,
And
Okay.
you said that you had an argument purely within the gravity path integral. That never made
Indeed.
sense. You will tell us about that as well?
Indeed.
this is the replica tricks.
Yes.
But then how will you get through all that in one lecture?
I also had possible lecture. I prepared material also for large black holes, but maybe I will not be able to get that.
You mean, without the radiation?
Without the radiation, just about the state dependence of, the nature of the dictionary for the black hole interior. But it is kind of a separate story from this thing. We don't have to talk about that. I just prepared it just in case.
One possibility is that you want tomorrow evening?
I just want to.
Yeah. I mean, do you have in mind how late in the evening would it be doable tomorrow evening? Just to ask you, not to inconvenience you all.
Maybe if we end by 6:30.
Okay. Let me just check 1 minute. And,
I'm available.
so like
Today?
Tomorrow.
Tomorrow in addition.
Does that work for you?
Oh, yeah, yeah. Even today, I mean, later works for me.
Today's better.
Any, no, I was supposed to have a class. We can postpone the class. Okay, fine. Today's fine. Yes,
Let's do tomorrow, if it's okay. 5:30 tomorrow. Tomorrow. What did you say?
5 to 6:30.
What about 5?
Oh, 5, okay, 5 tomorrow. Let's do 5 tomorrow if you don't mind. Morning also there is, morning also there is, but we'll have 5 to 6:30.
Sounds good.
Okay.
We're sorry to exhaust you.
Oh, no, this is a lot of fun. So,
Very good.
a lot of fun.
Very good, yeah.
Especially for me, I don't know anything.
Okay.